Hey, this is the first video in Chapter 4, 2D Motion, and my goal is to try to do Chapter 4 in 3 videos. The first video is to introduce the main concepts for projectile motion, circular motion, and relative motion, and then also to talk a bit about a few of the projectile motion ones. In the next video, finish up projectile motion and maybe do some circular motion. And then in the third video, finish up whatever is left over. So we'll see if I can do it. Alright, 2D motion. Well, the first type of 2D motion we're going to be doing is projectile motion. That's basically just motion, something flying through the air, and it has the usual parabolic path that we're used to seeing. And the thing about projectile motion that's going to make it easier to analyze is that we're going to separate it into a combination of we're going to separate it into x direction and y direction motions and then combine them to get where we need to get. In doing so, we're going to realize that there's no acceleration in the x direction unless we consider air resistance, and this means that x velocity is constant. We're also going to realize that, or we're going to consider the case where only gravity is acting in the y direction, so there is actual acceleration in the y direction from the force of gravity. And because of that, as something moves up, it slows down, and as it moves down, it speeds up, and at the very top of its path, the y velocity, the velocity in the y direction, is 0. There's an equation in the book. Let me actually look it up real quick. Yeah, it's equation 4-26 on page 67 of your textbook. I wouldn't recommend using this equation unless you're willing to memorize it. First off, it only works for when the launch height and the landing height are identical. In other words, maybe if you kick a ball from the ground and it lands back on the ground, if you have a projectile like off a cliff where you go whoa, and it lands down at the bottom of a cliff, that range equation won't work. And you can get that range equation just by using the kinematics equations. So I'm going to show you how to do that anyway. So unless you don't want to derive it with two kinematics equations, then you want to memorize this and remember that it only works for this case where initial or beginning and ending height are the same. You want to set up, I'm going to teach you how to set up a list of givens in the x direction and the y direction, and how the time in those lists of givens is the same for both the x and the y, because really breaking it up into x and y direction motions is just to simplify the problem. It doesn't mean that they're two separate things. It's really still one motion that's both in the x and the y always at the same time. So if it goes up this high in 5 seconds, it also goes over this far in 5 seconds. So it goes up this high, it also goes this far. So it's got a common point. You can think of that as components: y component, x component. And finally, for projectiles, oftentimes we'll set up these lists of givens and realize I don't have enough givens to solve for stuff. Remember, I've said a few times, I'm sure to each of you, that you need at least 3 givens to use the kinematics equations to find something else. And so if you don't have enough of those, then you'll have to use a system of equations, and which means just take 2 or more equations and use that to isolate one of the unknowns that you don't really need, so that you can solve for the unknown that you do need. Usually time is the link between the two, because time is the same for both. Going to circular motion, so this is now motion in a circle, which is also 2D motion, but different. Whoops, ignore that little curly Q. Now a little different than projectile motion. In this case, the speed around the circle equals the circumference around the circle divided by the time it takes to move around the circle. This could be for going around a circle once, twice, half a circle, whatever. It still works. And that's speed. If you want to discuss acceleration in the circular motion, then the centripetal acceleration you can solve for by using the velocity, which is this thing up here, divided by the radius, how far away you are from the center. And in addition to that, this gives you the magnitude, the direction, because acceleration is a vector. The direction is always pointing towards the center of the circle for centripetal acceleration. So if you're here, your acceleration is pointing that way. If you're here, it's pointing that way, etc. And for relative motion, which is a very tricky topic, I don't think the human brain was necessarily meant to think logically about this. So it takes some brain workings to get this going. But anyway, in relative motion, velocities and positions are relative, but accelerations are not, and I'll talk about why in the last video. And you can use, when you're doing two-dimensional relative motion, for example, let's say you're flying a plane and you point the plane north, but there's a wind blowing east, or I guess west in this case. Actually, let me just draw this over. So you're in a plane, and your plane is pointed north, but there's a wind blowing west. Your plane will actually follow this path right here, because its engines are pushing it that way, and the wind is pushing it that way. So this is you could say this is the relative path that you would take compared to the ground, and also this is the direction of your speed, of your velocity, I should say. So you can use similar triangles with 2D relative motion that has not acceleration. Am I Yoda? Let me fix that. Can you simulate triangles with 2D relative motion that has not accelerate? Oh, that was horrible. Don't do Yoda when you got a head cold. Maybe I should never do Yoda anyway, just in general. Anyway, so the third thing with relative motion is that you'll often see with respect to. And I couldn't really think of very good wording, so when I explain this in more detail, this should make more sense. But the best thing I could come up with was that with respect to means motion relative to something as seen from an observer not moving on that something. Anyway, I'll go into more detail on that later. Alright, so let's get through as many of the projectile motion concepts as I can before 15 minutes is up, and then I'll go to the next video. Alright, so projectile motion is a combination of x direction motion and y direction motion. Ding! So for the same reason that we broke vectors up into components in the last chapter so we can add them together easily, we're also going to want to break up vectors into components for projectile motion for similar reasons. It just makes dealing with the vectors much more easy, because if you use the actual velocity vectors, which for example are, let's say this is the actual velocity vector, blue here. This is the actual velocity vector at the initial position here. This is the actual velocity vector, which you can see is shorter and at a different angle. Shorter because gravity is slowing it down, at a different angle because it's the x velocity is now a larger percentage of the total velocity. Here, the actual velocity is only in the x direction because, as I discussed earlier, there is the y velocity is 0 here because gravity has stopped its upward motion completely. And again, likewise, same thing happens with the vectors here. They're always in different directions, so it just makes comparing this velocity and this velocity not impossible, but just not fun, not easy. So what we do is we break them up into x direction velocities and y direction velocities, and that makes life much easier, especially since gravity is acting completely in the y direction. If we were on some strange planet with some strange force acting, say, this way, then we might set up our coordinate system in that same direction so that this was the y-axis and this was the x-axis. But we don't live in that universe, and so we'll do it this way. And you can see some things which I'll talk about in the next slide. Let me just copy this picture. Oh, actually, I think. Yeah, so, ding! As you can see, if there are no forces, we haven't talked about forces yet, but you all know what forces are, and you know that forces can cause things to speed up or slow down. If you push on something, you can either speed it up or slow it down depending on the direction of your push. But in this case, as long as we consider that there's no air resistance acting in the x direction, then there are no forces. If there's no forces, we'll have a constant velocity. And that makes our life much easier because we know that this vector here, and this vector here, and this vector here, and this vector here, and this vector here, they're always in the same direction, and they're always the same length. Because this is a velocity vector, if the velocity is constant, then the length has to be constant. And yeah, so that's going to make solving problems much easier because we know that x equals v naught t plus, whoa, plus 1/2 at squared. We know that for constant velocity, there's no acceleration. This term goes bye-bye. And delta x equals v naught t. This is another way of writing v equals d over t. Here's our v, here's our d, and here's our t. So we can just use this simple equation. And it makes our x variables, our x givens, much easier to deal with. In the y direction, we do have a force called gravity. Gravity is always acting down. So if something is moving up, gravity is trying to slow it down and stop it from going up. But if something is moving down, gravity is assisting it and speeding it up. And so that's why you see the y vectors getting smaller on the way up until they reach 0 here, and then getting bigger on the way down and pointing down as you go farther down. So gravitational acceleration, which by the way is we'll use as 9.8 meters per second squared on the Earth, or if you're doing a multiple choice question where you don't have access to your calculator, I would just use 10, round that up to 10 meters per second squared. For web assignment problems where you have your calculator, use 9.8 because once in a while, if you don't, that will take you out of the tolerance of error for web assign. I guess I'll keep going here. Yeah, so don't use the range equation. I'm not going to keep going because I want to show you how you can get around using the range equation, or actually where the range equation comes from, and that's going to take longer than 2 minutes. So I'll stop this video here and continue this next time.